see a typo up here. It should be chapter 8.3, goodness of fit test. So the chi-square goodness of fit test, is a test that's used to fit this tests the model used to fit the data, okay, as opposed to the chi-square test for independence, tests the data itself. So what I mean by that is a good example for chi-square goodness of fit is an example would be see if a dice was fair. Okay, so if I were rolling a die 6 times and I have my list of probabilities from the dice rolls, or my list of outcomes from the dice rolls, a chi-square test for independence would be running the data on the test on the actual data. A chi-square goodness of fit test would be trying to match that data to what the expected outcomes are. That's the big difference. Okay, so chi-square goodness of fit is comparing the data to what's expected to happen. A chi-square test for independence is checking 2 variables and seeing if they are independent of each other. All right, that's really the goal. Okay. So in Arizona, somebody sent a mailer to everyone with a nuked photo of the city. Gosh, that's brutal. Yeah, that's messed up.
So we would be doing like the like instead of the chi-squared test, it'd be the chi-squared
goodness
Goff
of fit test. Yeah, Goff test. Yeah, the goodness of fit test. That's the big difference here from today versus Friday. All right. So the big things we need to do is we'll take a look at example 4. It's the students in 8th grade are asked what day of the week their birthdays are on this year, and then the table shows how many students were on each day. Write down a table of expected values given that each day is equally likely, right? Because you should expect that everyone has their 7 days of the week, right? There's 1 in 7 chance of getting them. So what we want to do first is we want to add up the total number of students. And then we're going to redistribute the expected value.
Mr. Street, can you share your screen?
No. I'm sorry about that. Thank you for bringing that up. All right. So you don't like just staring at me, huh? Okay. So there we go. Sharing the screen. So we're going to add the total students. 12 plus 14 plus 18, and we'll get our number. And it comes out to 105 students. Now we're going to divide by 7, because there are 7 days of the week. And we should get 15. So what this means then is if we have our day and our expected, I did not give myself a lot of room here. We're going to zoom in. I'm going to do this the right way. So we have our day and our expected value. We should have 15 students per day. So Sunday 15, Monday 15, Tuesday 15, Wednesday 15, Thursday 15, Friday 15, Saturday 15. That's what our expected values would be. Okay. Now we're going to conduct a chi-square goodness of fit test. So what I do have is posted on the Canvas page. I do have how to put the chi-square goodness of fit test in your calculator instead of a regular chi-square test. And basically the big thing is we need to what am I going to say? Oh, we need to put in table 1 is our expected outcomes, and table 2 is our actual outcomes, and then we compare the two. So I'll show you guys. So all three examples today do have calculator examples as well. So the first one is example 5. Let's see, I can pull this up. So all right, so first you're going to create your list 1 is going to be your actual outcomes. That's your actual outcomes. Your list 2 is going to be your expected outcomes. All right, so just make sure you get your list 1 and your list 2 correct.
What does the DF thing mean again?
Degrees of freedom. So DF is degrees of freedom. Okay.
So how do you do that one?
We'll talk about that when we get there. Okay, so we're doing a chi-square test with a 5% significance level. All right. So list 1, 12, 14. All right, so big thing here is you can graph this. This is something I haven't really talked about too much with us, but we can graph these things on scatter plots, and we can actually see the line of best fit, and that's a really good way to make sure that we're identifying positive versus negative if that ever becomes a problem. Anyway, so for chi-square goodness of fit, you should have your list 1, your list 2, and then it does ask for your degrees of freedom. So I guess we need to talk about our degrees of freedom a little bit here. Degrees of freedom in this problem should be 6. And it's always going to be one fewer than the total number of outcomes. So in this case, there were 7 days of the week. So it's going to be n is 7, so you do n minus 1. So I'm going to write that down for a note on my, I'll write that down as a note on my iPad when I switch back to it for you guys. But anyway, you should get something like chi-squared value is 1.6. And then you get your p-value is 0.952577, something weird like that. All right. And we'll go back to our iPad. So you get your chi-squared and your p-value. And remember that in order for us to accept the hypothesis, p has to be greater than 0.5. And this is 0.95 is greater than 0.05, so we are way above the limit there. All right. So remember, that's talking about with our null hypothesis and our alternative hypothesis. So the other big difference with these types of goodness of fit problems is the null hypothesis isn't going to be about independence anymore. The null hypothesis is that we expect the values to line up pretty generally, okay? So that'd be our null hypothesis. We expect there to be about 15 students on each day, all right? And then the alternative hypothesis is we don't expect that, okay?
So 0.95 is greater than 0.05. So it's...
So this, we're accepting the null hypothesis. Remember we said, last time I said at the very end of class, like, if the p-value is low, then reject the hoe. That's the null hypothesis. So we can remember that. If the p-value is low, reject the hoe. All right, and in this case, we're perfectly fine. We're super high p-value, 0.95. The critical value is 12.592, and we want our chi-squared value to be less than the critical value, which it is. So write down the conclusion for the test. So honestly, our conclusion for this problem is going to be that that the numbers do line up with the expected probability pretty well. All right. Mm-hmm. So the numbers line up with expected outcomes pretty well. All right, and then we had degrees of freedom, which I said we were going to make a little note of. I guess I didn't add that on here. So degrees of freedom are always going to be n minus 1. And the n is the number of outcomes. So in this case, it would have been 6 degrees of freedom. And again, the degrees of freedom are always thought of like you start with your first outcome, and then you say there are 6 other events that are independent of this one. That's kind of logically what's happening. You don't necessarily need to know that. All you need to know is that it's just going to be n minus 1 every single time. All right. That's example 4. Example 5. Scores for an IQ test are normally distributed with a mean of 100 and a standard deviation of 10. All right. Since Zia gives an IQ test to all 200 IB diploma program students in the school, her results are shown in this table. She wants to test whether these results are also normally distributed and performs a chi-square goodness of fit test at a 10% significance level. All right. So because this one's talking about, normal distribution, our null hypothesis would be that yes, the data is normally distributed. All right. I really like these chi-squared goodness of fit tests because your null hypothesis is always going to be the outcome is exactly what we expected. That's always your null hypothesis and these goodness of fit tests. And then the alternative hypothesis would be the data is not normally distributed, so it's not what we were expecting. Okay. Okay, find the expected values. I don't know why when I wrote this I didn't give a lot of space there. That's weird. All right, so the expected values would be based off of the normal distribution, right? So this one would require us to think back to our probability chapter to do that, okay, when we're looking for the expected values. So we would need to use normal CDF for this one. Okay. So you go to your calculation, or was it tests? So we go down to, where was it? It was in the stat button.
Second bars.
That's right, it was distribution, yes, thank you. And then we do normal CDF, and we're going to say, or set our lower bound, set our upper bound. And in this case, we can just use the, we can use the, what do you call it? The, 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 the lower bound is, the first one is negative infinity, and the upper bound is 90. Our mean is 100, and our standard deviation is 10. Okay, that would be the first one. So this is our mean of 90. Okay.
Wait, sorry, can you say that again?
Sure. So what's going to happen is we're going to find the expected values, right? And we're saying that the test is normally distributed. So what we're going to need to do is we're going to need to do normal CDF on this, which is that button on our calculator. And what we need to do is we need to find out the percentages. All right. So what happens when I do the first one, I'm going to get a percentage like 1.586552596, something weird like that. So that's the percentage that I land there. Now what I'm going to do is I'm going to do the expected outcome is there were 200 students, right? I'm going to multiply 200 times that 0.15866. That's what I'm going to do for expected values. So I'll do my score and my expected. So when x is less than 90, I ended up getting like 31.7 or something like that. That's how many students I expect. I can already tell you this is not looking good because the frequency is 5, but I'm at 31.7. So that looks kind of weird. And now I'm going to do normal CDF again for the second one. Between 90 and 100. So this time when I do normal CDF, I'm going to set my lower as 90, my upper as 100. And then I can go ahead and find it. And it gives me like a 0.34, so it's like 34% of this data is going to fall in that category. And now I'm going to multiply that answer by my 200, because there's 200 total students, so a certain number should fall in here. And I'm going to get 68.3. And then I keep going, and I'm going to do every single column like this. I think we go all the way up to 130. There we go. All right. So I'm going to fill all of them out and just keep doing that. So why don't you guys practice and fill out those few problems with your normal CDF. Make sure you're in this comfortable, and you're multiplying all of your percentage out, or all of your probabilities by 200 to get your expected value. 120 to 130 came out to 4.28. And then the last one, greater than, is 0.270. Okay, so that's our possible expected values. Okay. So now, part C says, write down the null and alternative hypotheses. Okay, so the null hypothesis is again. Yeah, we already did that. I think I had the wrong part C down there. Hold on a second. Yep. So that's the wrong part C. Sorry, that's a typo. So what part C is supposed to say is, if any expected values are less than 5, rewrite both tables. So basically what it wants us to do is it wants us to condense the table so all of your expected values have at least more than 5 students. All right. So let me show you. So this table over here with the frequency, it's fine because everything's at greater than 5, so that table's fine. But this table over here, I've got less than 5 students right there, and I've got less than 5 students right there. So what I'm going to do then is I can rewrite this table and say, here's my score, here's my expected value. The score is when it's less than 90, we had 31.7, so that's good. When it's between 90 and 100, we had 68.3, so that's good. When it's between 100 and 110, we had 68.3, so that's good. And now the next one, I have between 110 and 120, I had 27.2, that's fine. I'm going to add the 4.28 and the 2.7, or 0.7270. And that gives me, when I'm greater than 120, I should get 4.55, which is actually still below 5, because I wanted to add these 2 columns and just make a new greater than 120. But unfortunately, this is still below 5, so I actually need to do better than that. I need to go add this to the column above it. So I'm just going to say when x is greater than 110 here, and I'm going to say that 4.55 plus 27.2. And I get 31.75. So 31.7 or 31.75, we'll just put that. And that's how I do this when I rewrite the table, basically. It's just saying rewrite them so there's all the percentages are over 5, or all the expected outcomes are over 5 students. All right. Write down the number of degrees of freedom.
Mr. Straight, could
Yep.
you actually go back so you could see that, please?
Sure, sorry.
Thank you.
So yeah, now what happens then is we have the other table, score, and the actual students of frequency or whatever. We would do the same thing where we're going to go less than 90, between 90 and 100, between 100 and 110, and greater than 110. So we still had 5 here, we still had 14 there, we still had 74 there, but now with the last column we have to add all those numbers together, 54 plus 38 plus 15, which is basically all the students that scored greater than 110. We have to put them in that column now. So that way when we do the test, we have the same number of columns for both tables. That's why we have to rewrite it. But just by looking at the data, I can tell you, I have a feeling this is going to be pretty far off because look at our distributions here. We're expecting 31 students and we have 5. We're expecting 31 students and we have 107. We're expecting 68 students and we have 14. The only one that is somewhat close is the 68 to the 74. So I have a feeling that our null hypothesis will be rejected for this problem just by looking at the data, okay? That this distribution is not normal, okay? That's what I'm guessing. Okay, now the last part, write down the number of degrees of freedom. So because we consolidated it to 4 columns, the degrees of freedom should now be 3. Okay. Oops. So 1 less than the 4 columns, frequency columns we had before. Then we do the chi-square value, test statistic, and the p-value, and we're going to state our conclusion of the test. All right, so you
How did you just get that?
I'm sorry.
Since we have 4 that it's simplified?
Yeah, once we have it simplified to 4 columns, then the degrees of freedom is going to be 3 because it's always 1 less than the number of columns. Okay, or the number of, I should say 4 rows, sorry. We had 4 rows, it's 1 less than the number of rows, yeah. Okay. And now we can just run our chi-squared goodness of fit test on these 2 data sets. We just have to put the new stats in there. All right. What did we have for the last one? Was 107? 107, yeah, okay. Then we can put these numbers in on the other side. All right, once you get that all in, now you can do your chi-square goodness of fit test. You gotta know your degrees of freedom first, so we got 3 there. And bam, we get our chi-squared. So I end up getting chi-squared for this one. 244.48, something weird like that. My p-value, 1.02 times 10 to the negative 52. So it's still technically a decimal, it's just written in scientific notation. It's still a value between 0 and 1, but it's just in scientific notation. So for this one, we want to do 10% significance level. And I can tell you right now, this number is, whoops, times 10 to the negative 52. That is not greater than 0.1. That's way less than 0.1. And we can also see our test statistic is not less than the critical value. It's way over 6.251. So that means we reject the null hypothesis. This distribution is not distributed normally. All right, this data is not distributed normally. So that's the difference between chi-squared goodness of fit and the chi-squared test for independence from last time. The goodness of fit is we have an expectation of what the data should look like, and we're testing does it look like that. All right. The chi-squared test for independence last time was we just have 2 random things. Are they independent of each other? So that's the big difference between last time and today. Okay. But as you can tell, we got to be able to put these things in our calculator. Okay. Last example today, using what you learned in chapter 7, find the probability when you toss 3 coins of obtaining 0 heads, exactly 1 head, exactly 2 heads, and 3 heads. Okay. And then Hagar tosses the coin 200 times and marks a note of the number of heads each time. Her results are as follows. All right, so we have to figure out the expected outcomes of hitting when we're tossing 3 coins, finding 0 heads, exactly 1 head, exactly 2 heads, and 3 heads. All right, so this is another example. This is one that like the IB exam would love because you're using chapter 7 and you're using chapter 8 information. This is going to be a binomial distribution problem, and they even gave that to us at the beginning here. That's what this b, comma 3 and 0.5 is. Because we're talking about independent events. A coin toss is independent, right? So you're going to use binomial distribution first to find the expected values for the number of heads of each time. Okay. And what that's saying again is you're tossing the coin 3 times and you have a 50-50 shot each time. All right. So now I put in my binomial PDF because I'm doing exactly 3 coin tosses. Okay, whoops. And I put in the 3 and the 0.5. And it's going to give me an answer that looks like this: 0.125, 0.375, 0.375, 0.125 in my braces. All right. So this is the probability of 0 heads. This is the probability of exactly 1 head, the probability of exactly 2 heads, and the probability of 3 heads. Which makes sense that I'm going to have a higher probability of getting 1 or 2 than I am of getting all 3 of them or getting none of them. So that makes sense. And all of those probabilities should add up to 1 if I added all 4 of them together, because you're going to have an outcome of either heads or tails. Now we're going to multiply by the expected frequency, right? So we toss the coin 200 times. So expected frequency would be the number of heads, 0, 1, 2, 3, and expected frequency, I would do 0.125 times 200, 0.375 times 200, 0.375 times 200, 0.125 times 200. So just because I'm doing the coin toss 200 times, I'm going to expect to get those outcomes based on that. I get 25, 75, 75, and 25. And again, those numbers should add up to 200 as well, the 25, 75, 75, 25, because I should get my 200 outcomes on this table of values. Okay. And then I need to write down my null hypothesis and my alternative hypothesis. My null hypothesis for this problem, given all this information, is the number of heads will follow binomial distribution. All right. And that means my alternative hypothesis is the number of heads will not follow binomial distribution. All right, and again, just for this problem, the null hypothesis is like, what was the method I used to determine what my normal looks like, or what my expected outcomes look like? I used binomial distribution, so that's why I'm saying that's my null hypothesis. Okay, on problem 5, it was normal distribution is what I used, so that's where my null hypothesis comes from, is based on normal distribution.
There's 3 degrees of freedom, right?
Yeah, for this one, there's 4 possible outcomes, so the degrees of freedom would be 3, exactly. So my degrees of freedom are 3. Now I can find the chi-squared test statistic and the p-value. I'm going to give you guys a minute. I want you to figure those two out.